All right, today we're jumping into one of the biggest, most fascinating unsolved mysteries in all of science. Seriously, it's a question in computer science that's so important, there's $1 million prize for anyone who can solve it. But really, the answer could completely change how we think about creativity, problem solving, and maybe even genius itself. This is the P versus NP problem.
So let's just start with a wild thought. What if that flash of inspiration, that creative leap that leads to a brilliant new song or a groundbreaking scientific theory, what if that could be turned into an algorithm? What if a computer could discover a new mathematical proof just as easily as you or I could check the math on an existing one? That's the kind of massive, reality-bending question that's hiding inside P versus NP. And to wrap our heads around it, let's start with something we all know. You look at a blank Sudoku grid and, well, it's kind of tough, right? It could take you a good while, lots of erasing, a lot of trial and error to find the solution. But now, what if I hand you a finished Sudoku puzzle? How long would it take you to see if I did it right? Probably just a few seconds. You just scan the rows, check the columns, look at the boxes, and you're done. That huge difference. Finding the solution is hard, but checking it is easy. That's the core idea right there.
Okay, so let's take that idea and run with it. We're going to start by focusing on this whole category of problems that have this exact same quality. The solutions are a total pain to find, but once you have a potential answer, verifying it is a piece of cake.
Here's another perfect example. Pretend you're in charge of student housing at a university. You've got 400 students who need a room, but you only have 100 spots available. Oh, and to make it fun, you have a huge list of students who just can't be roommates. Trying to come up with a list of 100 students that satisfies everyone and breaks no rules, that's a logistical nightmare. But if your assistant comes to you and says, "Hey, I think I've got a list. How hard is it to check their work?" Super easy. You just go through the list and make sure none of the incompatible pairs are on it. Again, hard to find, easy to check.
So this brings us to the two stars of our show, the two big ideas or classes of problems that this entire mystery revolves around. Let's meet P and NP. Okay, so on the left you've got class P. Think of these as the easy problems. The P here stands for polynomial time, which is really just a technical way of saying a computer can solve it fast. You know, things like sorting a list of names or finding a number in a phone book. Now, on the right you have class NP. These are all the problems where if someone gives you an answer, you can check if it's correct really fast. Our Sudoku puzzle and the student housing problem, they live right here in NP. And here's the key thing to remember. Any problem that's in P is also in NP. I mean, it makes sense, right? If you can find a solution quickly, you can definitely check it quickly. Now, the full formal name for NP is non-deterministic polynomial time. It sounds intimidating, but honestly, don't worry about the name. The only thing you need to know is what it means in practice. A problem is in NP if you can quickly verify a yes answer, as long as you're given the right proof. That proof is sometimes called a certificate. For Sudoku, the certificate is the completed puzzle grid. For the housing problem, it's that proposed list of 100 students. And that brings us to the million-dollar question. This is the heart of the matter. We know for a fact that every easy-to-solve P problem is also an easy-to-check NP problem. But does it go the other way? For every single problem where the answer is easy to check, is there also a secret, easy way to find that answer in the first place? In other words, are these two classes of problems actually the same thing? Is P equal to NP? To get to the bottom of this, scientists found something absolutely mind-blowing. It turns out there's a special group of problems hiding inside NP that seem to be connected to everything else. It's like finding a single master key that doesn't just open one lock, but thousands of them all at once. These are called the NP-complete problems. You can think of them as the final bosses of the NP world. They're the hardest of the hard. But they have this incredible, almost magical property. They are all, somehow, the same problem in disguise. Any problem in NP can be translated into any one of these NP-complete problems. And what that means is, if you could find a fast, efficient algorithm for solving just one of them, you've done it. You've found a fast way to solve every single problem in NP. This is what we mean by a domino effect. And guess what? It turns out that plain old Sudoku is an NP-complete problem. So if you found a genius, lightning-fast way to solve any Sudoku puzzle, you could use that method to create a fast way to solve other things, like Latin squares. And that solution could then be transformed into a solution for a fundamental logic problem called 3-SAT. And that knocks over the next domino, which solves the even bigger satisfiability problem, which then, boom, gives you a fast solution to thousands of other critical problems in scheduling, logistics, medicine, you name it. One solution topples them all.
Okay, so now you can really see the stakes here. The answer to whether P equals NP isn't just some abstract puzzle for mathematicians. The answer would literally create one of two completely different worlds for us to live in. I love this quote from computer scientist Scott Aronson because it just gets right to the heart of it. If P equals NP, it means that finding a solution is no harder than checking it. That aha moment, that creative leap, would lose its special status. It would just be another calculation a computer could perform efficiently. And I mean, in this world, the upsides would be incredible. We could solve things like the traveling salesman problem to create perfectly efficient shipping networks for the entire globe. Computers could just start discovering brand new mathematical theorems all by themselves. We could figure out exactly how proteins fold, leading to cures for countless diseases. It would truly be an era of almost unimaginable progress. But, and this is a massive but, there would be a terrifying price to pay. Our entire digital world is built on a foundation of problems that are supposed to be hard. All of modern cryptography, the stuff that protects your bank account, your emails, your private data, it relies on NP problems being difficult to solve. If P were to equal NP, all of that security would just vanish. Public key encryption would shatter. The digital locks on everything from government secrets to Bitcoin would be completely broken. So we've got these two possible futures. One is a utopia of automated discovery, and the other is a cybersecurity apocalypse. So where does that leave us? What do the people who study this for a living actually think the answer is? Well, probably the single biggest piece of evidence we have for P not equaling NP is just a half-century of failure. For over 50 years, the smartest people in the world, the best computer scientists and mathematicians, have been throwing everything they've got at these thousands of NP-complete problems. And in all that time, for all those problems, they haven't found a single fast solution. Not one. That's a pretty powerful hint from the universe. And that massive effort, with no results, has led to a really strong consensus in the field. If you look at polls of computer scientists, the belief that P does not equal NP has just grown and grown over the years. By 2019, among the experts who really work on this stuff, 99% of them were convinced that P and NP are fundamentally different. The sheer importance of this question is why this number is on the screen. The Clay Mathematics Institute listed the P versus NP problem as one of its 7 Millennium Prize problems. They are offering $1 million for a formal proof of the answer, no matter which way it turns out to be. So let's end on this thought. If that 99% of experts are right and P really doesn't equal NP, what does that mean about the universe we live in? It would mean there are deep, fundamental limits to what we can ever hope to compute efficiently. It would mean that some problems are just intrinsically hard. It would mean that the creative act of discovery is truly profoundly different from the mundane act of just checking someone else's work. And it just might mean that true creativity, that human spark, can never truly be captured by an algorithm. Now that is something to think about.